Good day. My name is Shoikat Rai and my partner is Mir Faisal Tarif. We are presenting our advanced power system project titled Modeling and Control of a Bidirectional Battery Charger using Buck Boost Converter in Simulink. Our project was guided by Dr. Ashraf Ali Khan and the aim was to develop an efficient bidirectional battery charger system. Abstract. The objective of this project is to develop a bidirectional battery system that uses a buck boost converter. The main purpose is to demonstrate the proper bidirectional power flow for batteries using charging and discharging methods. The buck boost converter will allow a step up and a step down voltages, which facilitate varying power levels for energy storage applications. The project intends to use a control system to manage the current flow by monitoring the state of charge of the battery. A pulse width modulation (PWM) signal will be used for controlling switches to ensure a smooth transitioning from charging to discharging methods. The model will use a PI controller to calibrate switches and RLC circuit components. The design and implementation task will be completed using MATLAB Simulink. The Simulink model will illustrate the system's ability to manage power flows and maintain battery health, which will be appropriate for use in renewable energy systems and electric vehicles. The final output will focus on understanding the converter's capacity to maintain a consistent output under varying load situations. Introduction. Bidirectional converters are crucial for modern energy systems, particularly in applications like electric vehicles and renewable energy storage. These converters enable energy flow in both directions, charging the battery during low demand using buck mode and discharging it during high demand using boost mode. The buck boost converter is advantageous because of its simplicity and flexibility, adapting oil to varying input and load conditions. Our project incorporates PI controllers for accurate error correction and PWM for seamless mode transitions. Bidirectional buck boost converter operation. The bidirectional buck boost converter enables power transfer in both directions between a DC bus and a battery. It dynamically switches between two modes, buck mode for charging and boost mode for discharging based on energy requirements. Here we can see a basic circuit of a bidirectional DC to DC converter. In buck mode, the converter steps down the input voltage from the DC bus to a lower output voltage for charging the battery. The MOSFET switch Q1 operates with PWM control while Q2 switch remains off. The inductor stores energy during the switch on phase and releases it during the off phase, ensuring a steady current flow. In boost mode, the battery supplies the DC bus. Here, Q2 operates with PWM signal and Q1 switch stays off. The inductor stores energy when Q2 is on and releases it when the switch is off, boosting the output voltage. These operations are controlled through PWM signals, allowing precise voltage and current regulation. The converter ensures efficient energy flow whether the system is charging or discharging. System design. Our design uses a 800-volt DC bus, typical for high-power renewable energy systems and EVs, and a 360-volt battery. The power rating is 10 kW to ensure the system meets the charging and discharging demands effectively. A switching frequency of 5 kHz balances efficiency and performance. Key components like inductance and capacitance can be calculated using these formulas. Using this formula, we selected a 13 mH inductor for a smooth current flow and a 20 microfarad capacitor for stabilizing voltage. These parameters optimize the system for bidirectional energy transfer. Control block of converter. The control system is key to managing the bidirectional operation of the converter. Buck mode or charging mode. It uses positive battery current as the reference, indicating power flow into the battery for charging. The system steps down the voltage from the DC bus to the battery while maintaining a constant charging current. Boost mode or discharging mode. It uses negative battery current as the reference, representing power flow from the battery to the DC bus. The system steps up the battery voltage to meet the load demand. A PI controller minimizes the error between the reference current and actual battery current. A feedback loop continuously monitors key parameters like voltage, current, and state of charge to adjust the system behavior in real time. PWM signals are generated to control the MOSFET switches, ensuring smooth transitions between modes, stability, and protection against overcurrent or overvoltage. MATLAB Simulink model. The figure shows our MATLAB Simulink model. Our MATLAB Simulink model demonstrates the operation of a bidirectional battery charger. The system includes a DC source, battery, load, and a control block. During charging, the DC source powers the battery and load in buck mode.
Thanks, Shoykot Roy. Now I will take you through the second half of our project. The control block is the brain of our system. It employs a professional integral or PI controller to manage the charging and discharging process effectively. The PI controller minimizes error and ensures system stability. Additionally, the pulse width modulation or PWM technique regulates the transition between charging and discharging seamlessly. This control blocks plays a critical role in maintaining the reliability and efficiency of the battery charger, making it adapt adaptable to various load conditions. My next slide is for experimental result buck mode battery charging. As you can see in the plot, the charging current remains stable throughout the process. The battery voltage also follows a constant rate, which is essential for ensuring the health of the battery. Furthermore, the state of charge or SOC steadily increase as energy is stored in the battery. This result highlights the effectiveness of the charging system, demonstrating its potential for managing energy in renewable setups and electric vehicles. My next slide is for experimental result for boost mode battery discharging. Here, the current regulation is equally effective, ensuring that the load receives a stable output. The SOC decreases gradually, reflecting the energy being utilized from the battery. Importantly, the voltage remains stable even under varying conditions. This performance is crucial for application that relies on stored energy during period for high demand, such as during peak electricity uses or for powering electric vehicles. My next slide is conclusion. To summarize, our project successfully developed a Simulink model of a bidirectional battery charger. We demonstrated effective energy management for both charging and discharging mode. The result validated the feasibility of our design for use in renewable energy system and electric vehicles. Looking ahead, our future work includes implementing this system in hardware and exploring advanced control technique to further enhance its efficiency and adaptability. Here is the references where we collected our information. So thank you for your attention. I hope this presentation has given you insight into the potential of our project to contribute to sustainable energy solution.